next speaker is Nino Milani, and he will talk also about probably a little statistics.
Yeah, can you all hear me? Great, excellent. Yes, thank you. Great. And the pointer. Wonderful. Um, Good afternoon, everyone. My name is Nino Milani. I'm in the final year of my PhD project within the Paradise project, which is all about making life a little bit easier for analysts. And my part in that is in data analysis. Yeah. Okay, cool. So, as you all know, we have many ways of assessing our analysis. We can use internal standards or we can use external calibration, but it's much harder to assess how we're doing in terms of data analysis. So in general, there's sort of two approaches you could take. You could use your experimental data, which is of course the most relevant thing you can have. However, it requires quite an expert view to assess it, and even then it's an objective assessment at best. If you would like a more objective comparison, you would need to move towards simulated data. However, this is often criticized, and rightfully so, I think, for being not specific enough to your use case. If you can imagine, if you have a Gaussian in empty space, that's not going to tell you much how your data analysis is going to fare with your particular data set. So we set out to create a way to create a simulated data set while maintaining as much of the nuance from your experimental data as possible. So we started out with this beautiful GC-GC FID chromatogram. There's a lot of peaks in there, so we had a lot of stuff to work with. And we started with trying to find all the locations where there could be a possible peak, just using a general local maximum finder. And then we unfolded the chromatogram into its one-dimensional shape. So as you know, you can take the chromatogram, it's kind of like a carpet. If you take a string at the corner and you keep pulling, you get one linear string, but it's still exactly the same stuff as that carpet. And that's what you see over there. And then we fit all of the peaks that are in that one-dimensional shape. And we don't just use a Gaussian, we use a slightly different peak model called the skewed Lorentz normal. It's not that complicated. It's just two extra terms compared to a Gaussian. So you have the familiar position, width, and height. But we also have an E and an M parameter. The M is represents the peak shape. So that's something like, so that actually modifies the peak shape from a purely Lorentzian to a purely Gaussian shape, depending on the value. Whereas the E parameter is the asymmetry. So negative values are fronting peaks, whereas positive values are tailing peaks, and a 0 is an exactly symmetrical peak. And if we then do that peak fitting for all of the blue dots you see in the top middle figure, we get this out. And this is the actual simulated chromatogram. And as you can see, compared to the experimental chromatogram in the top left, they are very similar. However, the big difference now is that this is completely numerically defined. We know everything about all the peaks that are in there. And if you want, you could even start tweaking these peaks. So if you want to increase one peak a little bit more or decrease it a little bit, you can completely play around. And this allows you to use it as a sort of standard, like we've been doing for many years with chemical standards in the lab, but now as a standard for your data analysis. Now, this is work that's already been published, but I want to go one step further today and show you how we took the same approach, and rather than creating a benchmark data set, we created a enormous series of chromatograms in order to have a closer look at peak detection in general. So what we did, we took all this data, and rather than turning it back into a chromatogram, we made probability distributions out of it. And what these show is how likely it is to find a certain parameter for these peaks. So if we take asymmetry as an example, so the F, that is this one right here, you can see that the most likely value you find is a slightly tailing peak in this particular data set. And then we looked at the width in the first dimension, the width in the second dimension, peak ratio, so the difference in height, what that really means we'll get to in a moment, modulation shifting. So as you know, in GCGC, your modulations change slightly in second dimension retention time if you go further. The peak shape, so the M value, and the peak asymmetry, so the E value. And then we took all of these, created a lot of simulated data. How we did, we'll get to in a moment. And then we tested 2 different peak detection algorithms. And we chose these 2 implementations, not because we wanted to see which one was best, but because they represent 2 very different approaches in terms of peak detection. Because as the name implies, the 2-step algorithm works in 2 steps. It first detects peaks in a one-dimensional fashion, and then it starts to cluster them. Whereas the watershed algorithm keeps the data in a 2D representation and uses a more image-based approach to do it. So we wanted to see what these 2 ends of the approaches would give us. Now, how did we do the simulations? We created a series of chromatograms, which in each chromatograms there's a peak in the middle. That's the exact statistical average of all of these probability distributions. And then we have a moving peak, and this moving peak is also the exact statistical average, except for one value, which we changed each time. And for each of these sets, we created a position grid of 100 by 100. And then because it's simulated data, we can actually record the peak area that goes in and the peak area that goes out, and we can record a recovery. And then we end up with this figure that is slowly emerging on the right here. And this is a recovery heat map. And the colors represent how well the peak detection went. So green means we're very close to perfect. Warmer colors, so the reds and the oranges, represent an overestimation, whereas the cooler colors, the blues and the purples, represent an underestimation. Now here in the middle you also see a white area, and this is caused by scenarios where we put 2 peaks in and we, for instance, only found 1 peak out. Now, of course, there's not much use in calculating a recovery if your peaks are so close together that you can't distinguish this anymore, so white represents a failed peak detection. Now, what does a series like this looks like in reality? This is a series where in the top left, we move from very heavily fronting to very heavily tailing in the bottom right. So you see this blue cloud that appears here and then sort of centers around it and then starts moving to the bottom. And we are all chromatographic people, so we like to look at chromatograms to see what is going on. So if we would do that in a chromatographic visualization, you would see something like this, where here the black peak in the middle is our stationary peak, the one that doesn't move. And then we have 2 peaks which have the exact same shape, and their apices are the same difference, or the same distance from the stationary peak. However, if you approach a peak away from the tailing end, or you approach a peak at the fronting end, you can see that because we record the recovery of the moving peak, we end up incorporating part of this tail into the stationary peak rather than the moving peak. Because we simulate both peaks and we know the exact areas, we can see where this area ends up. And you might have noticed something, and that is that these chromatograms have these vertical lines in them. Even when we're very far away with these 2 peaks, we still have these lines. And we were quite puzzled by this at first, until we started to have a closer look at how the algorithms work. Now, as with any data analysis, we have to set a peak inclusion threshold, so to distinguish between peaks and noise. And even though there's no noise here, and we set it very, very low, we still end up with this scenario. And what is going on is that if we take a peak slice like this, we end up with all the modulations reaching above the peak inclusion thresholds. And so nothing happens and we find 100% of our area. However, because we can move in simulations our peaks so in such small intervals, we can move them in intervals smaller than the modulation time, and then you end up with sort of an in-phase modulation cutting or an out-of-phase modulation cutting. And you can end up with a scenario where part of your 2D peak, so one of your modulations, is so tiny that you don't include it. And that's what's happening with these vertical bars. Now, if I just take the top row and plot it as a function of the first dimension, you can see what is going on, and you see this pattern emerging that results from this effect. However, I also want to point out, because we're simulating, we can see very minute differences, because even the most extreme dip here is still 99.4% recovery. So this is something that in an experimental scenario would be quite hard to spot, because it's probably within the margin of error of your repeatability and this sort of thing. Now, we can look at these plots as a heat map, and then we have location information. But in this study, because we simulated over 700,000 chromatograms, two peak detection methods, that would still be 140 of these figures. And you would probably all be very bored by the end. We opted to also have a different type of representation where we sacrifice a little bit of the spatial information and gain some insights into the trends. So then you end up with a figure that looks like this, where the colors still mean the same thing. So white is a failed peak detection fraction, green is a successful one, blue is an underestimation, red is an overestimation. And then we zoomed in at the bottom 10%, and then at the top we have highlighted what the how much of the total peak detection was still successful. Because we're looking at a zoomed in version, it's kind of hard to see the overall trend. But this figure is very interesting because here we can see why the implementation of the two algorithms matters. Because in the two-step algorithm, because it has a clustering step, it has an inherent way of dealing with modulation shifting. And so if our modulations start to shift away from perfectly in line, there's still quite a bit of allowance where nothing really happens because it can deal with a little bit of shifting. However, as soon as it moves outside of this threshold for shifting, you can see that the error instantly shoots up. Whereas with the watershed algorithm, because it doesn't have an inherent way of dealing with the shifting, it's usually something you would deal with during pre-processing, you can see that this same change occurs. However, it's much more gradual, and by the time this one has left its capability, so to say, you are at roughly the same place as you would be with the watershed algorithm. Now, there's many more examples of this, and we are in the process of publishing this, so hopefully I can also show you the publication soon to show you all of the other nice figures. But for now, let's sort of give you a concluding remark. From all of the data that we generated, analyzed, and that we looked at, it is my understanding that there's not really a good or a bad peak detection approach. It's more about being aware of the characteristics of your data and the characteristics of your peak detection algorithm, so it's the quirks, so to say, and making sure that one doesn't influence the other in a too negative way. And on top of that, I think it's very interesting that we can use this approach to also create these benchmark data sets, which is a work that's already been published. It's also on our website, so if you want to play around with this simulated data, I highly recommend it, and I think it's a very interesting insight for anyone working with data analysis workflows. So a couple of people I want to thank. I want to thank Arjen, Bob, and Tijmen, who are my supervisors, Nart and Tesse, who are the two students who helped me with this work. Of course, our analytical chemistry group in Amsterdam, in particular Joska and Rick, who are also part of the Paradise project. The people who I work together with in industry, Ellen, Rob, Jan, and Gabriel. And of course, I want to thank you all for your attention. Thank you very much.